Okay, so today we will look at duality theory. I'll begin with the primal function. Let's go ahead and see what it is. Okay, so this is a constrained optimization problem. We have to minimize a function with respect to x, f of x, where f is a univariate function. So it's a mapping from n dimensions to, excuse me, it's a multivariate function, but it's a scalar function. So it's a mapping from n dimensions to scalar quantity and subject to the following constraints. So we have constraints of the form gi of x must be less than equal to 0. I is an index belonging to this set of inequality constraints. So gi of x less than equal to 0 is the general form of an inequality constraint. Likewise, hj of x equals 0, where j is an index of belonging to this set here is an equality constraint. So these are the equality constraints. Together, we have the inequality constraints and the equality constraints. And we have to minimize this function f of x subject to these constraints being met. Okay, and that's the general form of a constraint optimization problem. We define the Lagrangian of this optimization problem as follows. So L of x lambda mu. So we have x as the primal variable. This is what we want to minimize the function with respect to while meeting the conditions. And then you see two sets of variables or two vectors, lambda and mu. These are called Lagrange multipliers or dual variables. I'll use the terms Lagrange multipliers and dual variables interchangeably. So this Lagrangian is equal to f of x, the objective function, plus summation lambda I gi of x. So each lambda I is a scalar Lagrange multiplier corresponding to each of these less than equal to or inequality constraints, plus summation j of mu j hj of x. This mu j is a Lagrange multiplier corresponding to an equality constraint. And so we have one Lagrange multiplier for every inequality constraint, and we have another Lagrange multiplier for every equality constraint. Furthermore, for the inequality constraints, we must have lambda I greater than equal to 0. Mu j, the mu dual variables, can be positive or negative or 0, but lambda i's cannot be negative. Okay, that's when we follow this format. Now, if you were to rewrite the constraint optimization problem in another form, let's say you were to rewrite this as gi of x must be greater than equal to 0, then either we put a negative sign here or we must have lambda I less than equal to 0. It's your choice. But this is the general convention that we will be following in this course. Okay, all inequality constraints will be expressed in this form: gi of x is less than equal to 0, and likewise, this would the Lagrange multipliers. All these there will be positive signs here, and the Lagrange multipliers corresponding to these inequality constraints have to be greater than equal to 0. And the feasible set is this F is the set of all x's which satisfy the constraints. Okay, now in vector form, sorry, I skipped. Okay, in vector form, we can write the inequality and equality constraints in this manner. G, bold G now, it's a vector function. G of x is less than equal to 0, where G is a mapping from Rm to Rl. So all L scalar inequality constraints I have put together as this vector inequality constraint. Likewise, h of x is equal to 0. Here, h is a vector function. It's a mapping from Rn to Rm, where m is the cardinality of the set of equality constraints. I forgot to mention, L is the cardinality of the set of inequality constraints. And so the Lagrange multiplier, the Lagrangian Lx lambda mu can be expressed in this form. F of x plus lambda transpose g of x plus mu transpose h of x. And the feasible set is the set of all x's that satisfy all the equality and inequality constraints. So set of all points with g of x less than equal to 0 and h of x is equal to 0. And this lambda vector must be greater than equal to 0. Remember that, which means that every scalar component of lambda has to be separately greater than equal to 0. The primal function is defined as, so any questions about the Lagrangian? So the primal function, theta p of x, is simply the supremum with respect to lambda greater than equal to 0 and mu of the Lagrangian. So basically, we take Lx lambda mu and we maximize it over lambda and mu. So we get a function of x. Because once you maximize with respect to lambda and mu, we have eliminated lambda and mu already. And so it's some algebraic expression in terms of x. And that's theta p of x. And so this is also equal to, just putting in the value of Lagrangian in terms of f, g, and h, this is theta p of x. And in terms of the scalars, lambda I greater than equal to 0 and mu j, it's the supremum with respect to them of fx plus summation lambda iji of x plus summation mu j hj of x. So this is the primal function. What it is basically we take the Lagrangian. Remember that the original problem entails minimization of the objective, right? And the Lagrangian has fx in it, but what we are doing is we are maximizing with respect to lambda and mu. Okay, minimizing with respect to the primal variable x, as opposed to that, what we are doing is maximizing with respect to the dual variables, lambda and mu. Okay? And therefore, theta p is a mapping from R to the n to R, same as the objective function. Okay? Okay. Remember this definition of the primal function. It's very important. Okay, so more on theta p of x. So this is what we can formulate our constraint optimization problem as: minimize with respect to x of fx, where x belongs to f. F is defined as the feasible region, which was this one. This is the feasible region or the feasible set. I should have written, sorry for the typo, x belongs to f, where f is defined by this. Okay, so this is a shorthand notation for the same constraint optimization problem. Okay, now theorem 1. In the feasible region, this is the feasible region, the primal function is equal to the objective function. And in the infeasible region, the primal function is infinite. Okay, so theta p of x, when x is in the feasible region, that is, it satisfies all the inequality and equality constraints, then theta p of x is equal to f of x when x belongs to the feasible region. Otherwise, theta p of x is infinity when x does not belong to f. When x is infeasible, it either violates uh, uh, at least one of the inequality constraints, or at least one equality constraint, or maybe some equality and some inequality constraints. As long it doesn't satisfy all these constraints, then x does not belong to f. In this case, theta p of x becomes infinite. Let's prove this. This is an important theorem. Proof. So theta p of x is by definition equal to this. Supremum with respect to lambda I greater than or equal to 0 and mu j of f of x plus summation lambda I gi of x plus summation mu j hj of x. This is the definition of theta p of x, and we will be proving this theorem. In the feasible region, theta p of x equals f of x. In the infeasible region, theta p of x becomes infinity. Okay, so let's see how. So this is the definition. And then, since this supremum, when we are maximizing with respect to lambda and mu, this term f of x is independent of lambda and mu, correct? So we bring it outside this supremum operation. So this is theta p of x is therefore equal to f of x plus supremum of this summation lambda I gi of x plus summation mu j hj of x. So what does this statement mean in terms of this? See, theta p of x equals f of x when x is feasible. What would happen to the second term here, the supremum? Which means that the supremum would be equal to 0, right? If theta p of x is equal to f of x, then this supremum would be 0. That's what we're going to show when x is feasible. And when x is infeasible, what happens? Theta p of x equals f of x plus this. So this must be equal to infinity, correct? For this to be infinity. That's what we're going to show in the next slide. Any questions? So we will examine the two cases separately. First, we will consider the case where x is feasible. It belongs to the feasible region. And in the second case, we shall examine where x is infeasible. It does not belong to the feasible region. Case 1, x belongs to f, the feasible region. X is feasible. Okay, so all the constraints are satisfied by x, which means that every inequality constraint gi of x less than or equal to 0, this is satisfied. And every equality constraint aj of x equals 0. Okay, every gi of x is less than or equal to 0 for that value of x, any value of x in the feasible region, and hj of x must be equal to 0 for whenever x belongs to f. Okay. Now, gi of x is less than 0, and remember the corresponding Lagrange multiplier, lambda I, is greater than or equal to 0, correct? So gi of x is less than or equal to 0, lambda I is greater than or equal to 0. What happens when we multiply gi of x and lambda I together? What will be the sign?
It will be negative.
It will be negative.
Or 0.
Non-positive, right?
Yeah. Negative or 0, yeah.
So this implies that lambda I gi of x is less than or equal to 0. Okay. Now consider hj of x equals 0. Since x is in the feasible region, hj of x must be equal to 0. So what can you say about mu j hj of x? It must be equal to 0. For any value of mu j, the product mu j hj of x must be equal to 0, right? Okay. So what can you say about this? we're maximizing this. We will have to maximize with respect to the lambdas, right? But each of, you see the summation? Each term here is less than equal to 0, correct? So how will we maximize this? What's
Make it
maximum?
zero.
All lambdas will set to 0, right? Only then we achieve the maximum, which will be equal to 0. What about mu j, j of x? They're all equal to 0 because a j of x is equal to 0 in the feasible region. So it doesn't matter, whatever value, finite value of mu j we pick, these terms will all be equal to 0. So the summation of these terms will be equal to 0. And this, when we set lambdas equal to 0, then these will become equal to 0. Okay. Unless we need not set one of these lambdas to 0 if gi of x is equal to 0, right? Because that also would satisfy this. Gi of x is less than 0. In which case, by the way, lambda I will not be equal to 0. You'll see that later. But anyway, both terms, both summations are equal to 0. And that is the maximum. Whence the supremum is equal to 0. As long as x is feasible, this is equal to 0. And therefore, theta p of x, which is equal to f of x plus this supremum, is equal to f of x, because the second term here is equal to 0. Any questions?
Dr. Das, what's the difference between the maximize and the superior? It's the same, just like.
Yeah, you can, don't get confused. For functionals, I use supremum, but just for maximizing numerically, I use maximum. In this case, what will happen is what this will return will be a function of x, right? It won't be a numerical value.
I understand, yeah.
Okay, so that's fine. I'll show you plenty of examples, by the way. So we just show that when x belongs to the feasible region, theta p of x is equal to f of x. Next, for case 2. What is case 2? Remember? When x is infeasible, what happens?
Infinity, it's said to.
Infinity. The primal function theta p of x becomes equal to infinity. Okay, so this is the first part which we just established. So when x is infeasible. Now, x, when we say that x is infeasible, at least a constraint, at least one constraint must be violated, correct? And that constraint could be either one of the g's, inequality constraints, or one of the h's, inequality constraint, right? So let's examine the first case. Some gi of x is greater than 0. Okay, it must be infeasible, and let's assume that that's because some gi is not less than equal to 0. For some gi, it's greater than equal to 0. Okay, so this is case 2. X does not belong to f. At least one constraint is violated, and suppose a gi of x is violated. That's what we will look at first. Now, what happens then? Lambda I is greater than equal to 0, and gi of x is greater than equal to 0, correct? What happens to the product? Lambda I gi of x. It's always non-negative, right? Positive or 0. So lambda I gi of x is greater than equal to 0. In which case, what happens? What happens to the supremum? Just ignore the other terms. What will happen to this lambda I gi of x? We are trying to maximize with respect to lambda I, and lambda I gi of x is already greater than equal to 0, right? They're of the same sign. So what would we do? We set lambda I to be equal to
infinity.
Infinity. And so this term will be infinity. Just forget the other terms. Theta p of x becomes equal to infinity in that case. Agreed? So if a inequality constraint is violated, then we can set the corresponding Lagrange multiplier lambda I to plus infinity. Lambda i's are always restricted to be greater than or equal to 0. So we set it to plus infinity, and so theta p of x becomes equal to infinity. So that lambda I equals infinity. So lambda I gi becomes equal to infinity, whence theta p of x becomes equal to infinity. So we just show that when gi of x is violated, theta p of x equals infinity. Now we have to look at the other situation where an equality constraint is violated, right? We're still in case 2. Case 2 has 2 parts. An inequality constraint being violated, and the other part is of case 2 is an equality constraint being violated. So let's look at an equality constraint being violated. So we proved the first part of case 2. Now let's look at the second part. Now suppose an hj is violated. Okay, which means that hj is not equal to 0, right? Because this is what the constraint is. Now remember that mu j can be of any sign. Okay, hj of x is not equal to 0. So since mu j can be plus or minus, we'll let the sign of mu j be equal to the sign of hj, so that mu j hjx is greater than 0. Okay, we choose some non-zero mu j of the same sign as hj. Okay, hj is not equal to 0. And so mu j hj is always greater than 0. It's strictly greater than 0. So what happens to theta p of x equals f of x plus, just look at this term. We have to maximize with respect to mu j of this. What do? We set mu j equals infinite. And so this term becomes equal to infinite, right? Correct?
Yes.
And so mu j hj becomes infinite when theta p of x becomes equal to infinite. So this is the other situation, other part of case 2, where an inequality constraint is being violated. Okay, so we just show that in the infeasible region, theta p of x is equal to infinite. We can maximize with respect to mu's and lambdas in such a manner that theta p of x hits infinity. But we cannot do that in the feasible region. Okay, so we just proved this. So this is just a graphical illustration of what we just proved, theorem 1. This is the function. Okay, this is the maximum of the function, correct? Just visually, this looks like the maximum of the function. Oh, sorry, we are looking at minimum. We want to this is a function f of x, and we want to minimize it, right? This is the absolute minimum of the function, the global minimum, but it's not in the feasible region. This green shaded region is the feasible region. And this, you see that the blue curve is f of x, and the green shaded region is the feasible region. The x-axis is this. Okay, this is the feasible region. The gray shaded regions are infeasible. And this, in the feasible region, theta p of x equals f of x. You see that? The red dotted line is theta p of x. In the feasible region, it's equal to f of x, right? But in the infeasible region, it shoots up to infinity. So everywhere here, it's infinity. Theta p of x is infinity everywhere here and here. Okay? Any questions?
No.
How about the other guys here?
No
No
questions,
question.
Dr. Das.
No question.
So we define the primal function. Now, theta p. Now, the primal problem. Okay, theta p of x is supremum of, with respect to lambda greater than equal to 0 and mu of the Lagrangian, Lx lambda mu. And we just proved that theta p of x is equal to f of x, the function, objective function that we want to minimize when x is feasible, and it's infinity when x is infeasible. The primal problem is minimize theta p of x. Okay. And what will happen? Minimize theta p of x. Now, theta p of x, obviously, when x is infinity, it is infinite. We want to minimize this function, theta p of x. So when x is feasible, theta p of x is finite. In fact, it's equal to f of x, correct? So when we minimize, we automatically constrain x to be feasible, and then the minimum of this would be equal to the minimum of f of x. Okay, so the primal problem is this: minimize theta p of x. And it removes the constraint. So what we have done is the constrained optimization problem has been reduced to an unconstrained optimization problem, a simple unconstrained optimization problem. And as a result of theorem 1, the solution to the primal problem is the constrained optimum, which is x star. And the minimum of the primal function is denoted theta p star, and that will be equal to f of x star. So x star is argin of theta p of x, which is argin of this. I plugged in the expression for theta p of x here in terms of the Lagrangian, and theta p star, this is convention, is equal to theta p of x star. Okay, so the solution to the primal problem is the constrained optimum. Okay, so this introduces a nice technique. If we can construct the Lagrangian and somehow using differentiation or any algebraic manipulations, if you can somehow eliminate or maximize with respect to lambdas and mu's, then we get some function of x, that's theta p of x, and then we simply find the minimum, unconstrained minimum of that function, theta p of x. Okay. So this in our graphical illustration, so this is the constrained minimum x star. Okay. This is the primal function, theta p, and it's infinite outside the feasible region, and within the feasible region, the minimum is x star. Okay, the next is the dual. If we finished off with the primal, now let's look at the dual. Do we have any questions? Please free to ask me any question at all.
No, it's clear.
Okay. So next is the dual. Again, this is the constraint optimization problem in vector form. So we have to minimize the objective function f of x subject to the inequality constraint. G of x is less than equal to 0, and the equality constraint h of x is equal to 0. The Lagrangian is expressed in this form. Lx lambda mu is f of x plus lambda transpose g of x plus mu transpose h of x, and lambdas must be greater than equal to 0. And this is our feasible set, which satisfies all these constraint, or I've written this in terms of the scalar constraints. The dual function is minimize with respect to x. Okay, so here we minimize the Lagrangian with respect to x. And so once we do the minimization with respect to x, we eliminate x, right? And so what we are left with is a function of the lambdas and mu's. That's the dual function. The dual function is a function of the dual variables, lambda and mu, which is equal to the infimum with respect to x of f of x plus lambda transpose g of x plus mu transpose h of x. Okay. And in terms of scalars, it's equal to this f of x plus summation lambda I gi of x plus summation mu j h j of x. Now let's look at the dual function more carefully. First of all, it's a mapping. We have L inequality constraints and M equality constraints, right? And so it's a function, this theta d is a function of lambda, which is L dimensional vector, and mu, which is an M dimensional vector. So it's a mapping from L plus M dimensions to R. Okay, so this is the definition of the dual function. You see the contrast. What were we doing in the primal function? We were taking the supremum with respect to lambda and mu of this Lagrangian, right? And now we are taking the infimum with respect to x. Okay, so that's the dual function. Theorem 2, the dual function is concave. Okay. Hence, for any alpha between 0 and 1, so the dual function is obviously a function of two sets of variables, the lambda and the mu, right? So we have to show concavity with respect to lambda and concavity with respect to mu. Now, this is what a concave function looks like. This is x1, x2 for any alpha between 0 and 1. This is alpha x1 plus 1 minus alpha x2 is this here. Now this is some function f of x. This is f of x1, x1, f of x1, x2, f of x2, right? And this is alpha x1 plus 1 minus alpha x2, and this is f of alpha x1 plus 1 minus alpha x2. And if I take this here, join these 2 points with the straight line, and then this point is alpha times x1 plus 1 minus alpha times x2, f of x2. So this is f of x1 and f of x2. Okay, and so we have to show this. Now, I've color-coded these. So this, instead of f, now I have theta d. Okay, and ignore the mu when we are looking at, if we have to show concavity with respect to lambda, we just ignore the mu here. So we have to show that theta d of this blue here, alpha lambda 1 plus 1 minus alpha lambda 2, which is instead of x2 here, comma mu, is greater than equal to this alpha times theta d of lambda 1 mu plus 1 minus alpha theta d of lambda 2 mu. Am I clear?
Yes.
Yes.
And likewise for mu. Now we ignore lambda, and we, instead of mu, we replace it with alpha mu1 plus 1 minus alpha mu2. And we have to illustrate this. I will actually prove concavity with respect to lambda and leave it as an exercise for you guys to prove concavity with respect to mu. Okay, so let's begin. This is a fundamental property of the dual function. Now, note that I never said that f of x, the original objective function, has to be convex. Okay, I didn't say that. So it might not be convex, but this will be a concave function, theta d of x. Okay, so we're going to prove concavity with respect to lambda. So we're going to prove this. We begin with this. The definition, theta d lambda mu equals infimum of f of x plus mu transpose h of x plus lambda transpose g of x. Okay, and we let lambda be equal to alpha lambda 1 plus 1 minus alpha lambda 2, where alpha is between 0 and 1. Okay, and so this becomes equal to infimum f of x mu transpose h of x. Now this lambda is replaced with this alpha lambda 1 plus 1 minus alpha lambda 2, and then we have the transpose g of x. Okay, next what I'll do is, you see this alpha and 1 minus alpha, right? This f of x, this term and this term, I'll again split into two. Alpha f of x and 1 minus alpha f of x. And I'll do the same thing with the second term too. Okay, so this is equal to, you see this f of x here, I've replaced it with alpha f of x plus 1 minus alpha f of x. This mu transpose h of x, I've replaced with alpha mu transpose h of x plus 1 minus alpha mu transpose h of x. And then this alpha lambda 1 transpose g of x, and then 1 minus alpha lambda 2 transpose g of x. Okay, you guys are with me, right?
Yes.
So now what I'll do is I will club all the terms containing alpha together, this term, and this term, and I'll club all the terms containing 1 minus alpha together, second, fourth, and sixth terms. So this is equal to, we're still looking at theta d lambda mu, infimum of with respect to x of alpha fx plus alpha mu transpose hx plus alpha lambda 1 transpose gx plus 1 minus alpha f of x plus 1 minus alpha mu transpose h of x plus 1 minus alpha lambda transpose g of x. Now, if I were to take this alpha common here from the first three terms, what would I get? Any guesses?
The original concave,
Alpha
the
times
function?
the original
theta,
equation.
alpha times theta d of lambda 1 mu, correct? If I take this common, alpha common, fx plus mu transpose hx plus lambda 1 transpose g of x is simply L of x lambda 1 mu, correct?
Yes.
Yes.
And likewise, if I take 1 minus alpha common from the last three terms, I'm left with 1 minus alpha and this Lagrangian x lambda 2 mu. Okay, and so this is theta d lambda mu. I've divided it into two separate terms, two Lagrangians. Okay, alpha times this Lagrangian plus 1 minus alpha times this. And I have to do the infimum. I have to minimize the sum of these two functions. Correct? Now, if I minimize two separate functions simultaneously, like sine square x plus e to the log e to the cosine of x, okay, will I get a lower value? Or if I minimize the first term separately and the second term separately, sine square x separately I minimize and e to the power of cosine of x separately, I minimize and add them up together, I'll get another value. Which of them will be lower?
If I make everyone separate, I guess.
Separately, if I minimize, I'll get a
Yes.
lower value, right? That's common
Yes.
sense. And so that's what I invoke. So this, if I minimize both separately, alpha times, these are all fractional quantities, both greater than 0, right? Because alpha is between 0 and 1. So if I minimize this separately and this separately, I'll get a lower value. So this, what I landed up with, theta d lambda mu is greater than equal to alpha times infimum of this term plus 1 minus alpha times infimum of this function. Okay. And so what is this? Infimum? Theta d lambda 1 mu. By definition, right? And this, by definition, is infimum with respect to x of the Lagrangian, gives us the theta d, right? And so this is theta d lambda 2 mu. And so I just showed that theta d lambda mu is greater than equal to theta d lambda 1 mu plus 1 minus theta d lambda 2 mu. Going back to this slide, so this is what I just showed. It's concave with respect to lambda. Theta d.
So, Dr. That's here we are just trying to prove that the function is concave.
Yes.
And this property that we proved is just holding true for the concave function?
Yes.
Okay, thank you.
Sorry, I probably didn't emphasize that. Yeah, so for a function to be concave, this green should be less than equal to the blue. Okay. I should have mentioned that. I probably skipped that little thing. Okay. Now, concavity with respect to mu is practically identical. So I have omitted that part of the proof. Okay. The other way to show this is now an equality constraint can be viewed as two inequality constraints. So h of x equals 0. Okay, you can actually reduce or eliminate this equality constraint by replacing it with two inequality constraints. H of x is less than equal to 0 and negative h of x is less than equal to 0, which automatically means that h of x has to be equal to 0. Okay, and in which case we already showed concavity of theta d of lambda mu with respect to lambda. So instead of a mu, you'll have set of two lambdas here, right? Okay. So this is the dual problem now. Maximize with respect to lambda and mu of this theta d lambda mu. And the maximum of the dual function is maximum will occur at lambda star and mu star, and that is arg sup of inf of the Lagrangian. Okay, and theta d star is the notation theta d of lambda star mu star. Okay, so this is the dual problem. Now, x star, this we have shown previously. X star equals arginf, the infimum of the primal function, and we get this value, theta p star. So this is supremum with respect to lambda mu of the infimum with respect to x of the Lagrangian. Okay, notice the difference. What are we doing here? We are doing the we're taking the Lagrangian, focus on the dual. Okay, we're taking the Lagrangian, finding the infimum with respect to x, and then finding the supremum with respect to lambda and mu. Here, we are doing the opposite. We are first sorry, this is, I swapped the order. This should be, we take the Lagrangian, first we do the supremum with respect to lambda mu. And then we do the infimum with respect to x. This is a typo here. The inf and the sup, we have to swap the orders. Okay. Now, theta d star has to be less than equal to theta p star. Weak duality will always hold. Okay. Why? This is trivial to show. If you maximize first and then minimize, okay, then you'll get a higher value than if you minimize first and then you maximize. It's called the minimax theorem. Okay, and I'll prove it shortly. But so this, just remember, there's a typo here. So this is inf and then sup. We inf comes here, okay, to the left. Just swap the order of the inf and the sup here. That's a typo. Okay, and so this by default holds, and we'll shortly prove that. And then, furthermore, if this condition is satisfied, I'll show you what the latest condition is, then theta d star equals theta p star. And I have a graphical illustration of that too. Okay, so this is weak duality. Let's just prove weak duality. The infimum of the dual is less than or equal to the supremum of the primal. Theta d star is less than or equal to theta p star is what we have to show. Okay. Now we first begin with this. We take the Lagrangian. The infimum with respect to x of the Lagrangian is obviously less than or equal to less than the Lagrangian, right? Because we're explicitly doing the minimization, right? Therefore, I put supremums on both sides. The supremum with respect to lambda and mu of this side of Lx lambda mu is less than or equal to supremum with respect to lambda mu of the same Lx lambda mu, right? Now, if this value is so what does this statement mean? For every value of x, okay, this right-hand side is always greater than or equal to the left-hand side for every possible value of x, correct? In particular, even if you were to minimize with respect to x, this less than or equal to will still hold, correct? So if this left-hand side is always less than this function here of x, then it must also be less than or equal to the minimum of that function of x, correct? And so I just showed weak duality. This is theta d star and this is theta p star. Okay. This is what I showed. And so the difference is called the duality gap. And Under certain conditions called constraint qualifications, those would be sufficient conditions for strong duality, in which case the duality gap is 0 or theta P star equals theta D star. This is called strong duality. One possible constraint qualification is called Slater's condition. This is Slater's condition. The condition is there exists a point x naught such that all inequality constraints are strictly satisfied. So for every inequality constraint gi of x, this must hold. Okay. And then theorem 4, if the objective function and all inequality constraint functions gi of x are convex and equality constraints are affine, all equality constraint, these functions are affine. I'll tell you what affine is, and Slater's condition is satisfied, then strong duality holds. Mathematically, so f is a convex function, gi, each inequality constraint is also convex, and the equality constraints are of this form. This is an affine function. It's a linear function of x with a constant term. Okay, all h of x's are of this form, and Slater's conditions are satisfied, then strong duality holds. This is Slater's condition. There exists, this is the notation for there exists. Just like this is the logical notation for all. So there exists an x naught, which is strictly in the interior of the feasible region. Okay, and the equality constraints are affine, then theta P star equals theta D star. And this we will do without proof. Okay? So this is, let's summarize. So this is the primal function, theta P. And this need not be convex, okay? Although I've drawn it in that manner. And so this is the x-axis. This is where it's at a minimum. Theta P of x is at a minimum. Theta P star. This is theta P star. Now this is the dual. And it's a function of lambda and mu. Okay, so this is the dual. And I've drawn it along. This axis represents the lambda comma mu axis, okay, just for simplicity. And this is the dual, theta d of lambda mu. It's a function of the dual variables. Okay, and this, the maximum of this is at this point here, that's theta d star. This is theta d star and this is theta d star. Okay, and so this point here and this point here will touch one another if Slater's condition is satisfied, if strong duality holds. Okay. So this, the minimum of this blue curve here and the maximum of this red curve here will actually touch one another. And then that point will be called the saddle point. Okay, so when strong duality holds, so this is the lambda mu axis. Okay, so we are maximizing with respect to lambda and mu, and this is the x-axis. We are doing the minimum with respect to x. So this point here is a saddle point. It looks like a horse saddle, right? That's x star, lambda star, mu star. Okay, and it's very easy to establish Slater's conditions, by the way. So in most cases, simple cases, strong duality will hold. Okay. Now, I know this whole picture is quite confusing, but examples will illustrate the point. Okay? Any other questions?
No.
Okay, nothing at all. Okay, so what I will be doing is I'll be posting something in the message board and you guys will respond. Okay. So shall we quit?
Dr. As, I have just a question for the homework, if it's possible to ask now or.
Okay, I was going to post like when will you guys be free so that we can do a tutorial?
I don't. Did you do?
I will
Did you
post.
have? Did you have any tutorial before? Because I didn't get any notification for tutorial before.
No, I will post it.
For the new one.
Yeah.
That will be the second tutorial, right?
Yeah.
Dr. Das, there's also this is the first lecture in the B section, or it's the second? It's the second one, right? As I see, yeah, the first one is not published because I couldn't attend the last time.
Oh, okay. I'll look into it.
Thank you so much.
Bye.
Have a good day. Bye bye.
Thank you, Dr.